So the last two classes, or excuse me, last two homeworks. Yeah, I know. I'm sorry. I was realizing as soon as you raised your hand, I knew it. You don't want to see it anyhow, do you? Don't you want to imagine what it looks like? Hold on, we got to send to L projector. It's warming up. So I can't emphasize this enough. So one of the things that I strongly encourage, and I know it's difficult because in a modern world, we have computers that will do this for us, right? But these last two homeworks that are about these integration techniques, particularly these integrals that are time consuming, you should still, I knew I could count on you, Shay. I knew it. I knew you'd be here. Didn't I say you'd be here? Anyhow, so I am encouraging you to do your best to suffer through it. Make sure you know how to do them. Now, I can't force you to do that. And as I've said before, I can't force you or restrict you from going to the internet and using Wolfram or Mathway or one of these websites. But I got to be honest, if you're looking to gain anything from this class other than just credits, then my advice is to do your best to learn how to do these things. Okay, so good. What we're going to do today is sort of piggyback off that, but in a different way. So here's the moral. Integration is not always straightforward. Now, let's be very clear. We have to be specific by what we mean with this. That is determining an antiderivative is usually challenging. So that's really what we've done on the last two homeworks. If you look at them, except for maybe the one or two problems at the end, everything we've asked you to do is to determine an indefinite integral, which means you're really finding an antiderivative. Now, when we do those applications, like if we're finding volumes, or if we're finding arc lengths, or if we're finding any definite integral, then the problem is twofold. Because you can't get anywhere, well, I shouldn't say it's twofold, that's a bad way of saying it. Okay, let me back that up. That was kind of a weird way of saying it. But the fact of the matter is in order to even compute definite integrals, we have to be able to determine antiderivatives. So it's worth writing this on the next page. So don't forget. When we write something like this, this means g prime of x is derivative of g is f of x. So that is g is an antiderivative of f. So you're going to have to, if you don't remember what this means, you're going to have to go back to chapter 4 and 5 in your book, but this is really a Calc 1 thing. This notation, the last couple homeworks, what we've been doing is we've been asking you to determine antiderivatives. And we see this as difficult. And why do we do this? So why do we care? Well, if we, oh, that was ugly. So if we can get this g, the fundamental theorem of calculus says then the definite integral is just this antiderivative evaluated at the endpoints. So I don't want you to lose this. This is, you know, we defined this thing at the bottom, this definite integral. We defined this back in Calc 1. We motivated it through this idea of area. And from then, since then, we realized that it can tell us volumes. It can tell us arc lengths. It can tell us velocities. It can tell us positions. It can tell us surface areas. It could tell us hydrostatic forces. There are literally endless applications of the integral. We only touched a small piece of them. And so that is one way of saying that being able to compute this number is a very important thing. And the bad news is that it's important and it's also often hard. It's difficult. Does anybody have a comment about that or a question? Now, here's something you might not have thought about, or so we might say, is there another way of computing this thing that doesn't use the definition or the FTC? Right, that might be something you're interested in. You might say, oh, Grady, what we've been doing is hard. It doesn't seem practical. It's tedious. We already said numerous times how the definition is completely fruitless in that it's that big, complicated limit. Here's another question. Does an antiderivative always exist? You may be under the impression that if you suffer through enough torture, you can find these antiderivatives for every function. You know, this is sort of analogous to your high school algebra. In high school algebra, you learn these techniques for solving linear equations. Then you learn the quadratic formula for solving quadratic equations. And then you talk about polynomial equations, and you learn these things like synthetic division and factoring. And in many ways, you might be misled in that can solve any equation. And it's very rarely taught to you that that's just not true. In fact, most equations that you encounter that have degree 3 or higher cannot be solved using those techniques. Now, integration is much the same. Turns out there are many functions whose antiderivative exists but we can't express it in terms of our familiar, what we call elementary functions. And that was poor English. This should be antiderivative exists. Maybe I should say does exist. That reads better. Now, you're going to say, well, if it exists, why can't I tell you what it is? Well, we can. We just have to write it in terms of what we call a non-elementary function. Now, I don't want to get into that. That's for other courses. But the fact of the matter is there are certain things that I can ask you to determine the antiderivative of, and it's impossible. So here are two famous examples. The first one is e to the power minus x squared. And another one is, say, the integral of sine of x over x. So let me give you an example. So one of the things people like to do in 2020 is you like to go to the internet, right? And so suppose I go to the internet. Let's say I go to the Google machine. Hopefully everybody is seeing this right now. And let's go to Wolfram. Now suppose I ask Wolfram to integrate these things. Integrate e raised to the negative x squared. And you'll notice what Wolfram does is it tells me it's 1/2 the square root of pi, and then it says this thing you've never seen before, ERF of x. It's called the error function. Now, you guys likely have come across this before, now not in this context though. If you've ever taken an elementary prob and stats course, and you ever had to understand these z values and you had to go to the back of the book and look up these numbers and you had no idea what the hell it meant, but you just did it because that's what you did in prob and stats. Have you ever done that before? You're using this error function there. So if you want, you can Google the air function and read about it, but it's what we call a special function. It's not a traditional elementary function. If you look at this, the air function is defined as an integral, right? Okay, now what if I ask it to evaluate this from, say, 0 to 1? Now it's just going to spit out some decimal. And so the obvious question that I would ask if this were me is, how the hell did it get that decimal? And notice it didn't say it's equal to it. Notice it says it's approximately. So let's change this function real quick. Let's, instead of this square, let's go to something we could integrate. You'll see that if I do this function, which I could integrate, it tells me the exact answer, which you could get by hand. And then it also tells me an approximate answer. I don't know why it just disappeared. It wants to get more. No, I don't want to pay you fools. Go back, you jerks. So it gives me the approximate answer. Now, if I go back to the problem we were yapping about just 10 seconds ago, this particular integral, if I have a square on here, I cannot determine an antiderivative of this. So since I can't, I just give this integral name. It's called the air function. But then the question is, if I don't know what this means, how the heck do I get this number? Right? So what Wolfram is suggesting to us that there's got to be some other way out there that we can do things. Let's look at the other example I suggested. Let's look at sine of x divided by x. So let's ask Wolfram to integrate this, and you'll see it spits out this SI of x, which is, again, not an elementary function. It's called the sine integral. You can Google it and read all about it. Now, if I ask Wolfram to integrate this from 0 to 1, it's going to spit out a number. And the question is, how does it get that number? Does anybody have a question or a comment? All right, so let's remind you of the point I'm trying to make. So Wolfram is suggesting there must be a way to approximate definite integrals. That's what it's suggesting. That little sort of investigation we just did, that's one of the things we gained from that. Now, of course, we already know this. We know a very crude way of doing this. So we sort of knew this. And what do I mean by that? Just use Riemann sums. But there is a downside to using Riemann sums. And it's important we point that out. And that is the downside to Riemann sums is that you typically need a large sum for what we say a good approximation. So let's just rattle off a quick example of that. It's something we're familiar with. Before we do that, look, I hope you understand that what's important about what we're going to do is this time I've been spending the last 20 minutes trying to set the scene. Integration is difficult. Sometimes it's not just difficult, it's impossible. At least the techniques we've used thus far. And so what we're asking then is if we can't get the integral exactly, can we approximate it? And if so, how do we do it efficiently? Now, you might not realize that. Some of you might just say, well, just plug it into a computer. That's not always the case. Even computers have to work, and they require energy. You should feel how hot my computer is right now, because it's zooming, it's got its camera on the processor, I'm writing on this board, there's a lot happening here. Computers, we want to be efficient for them too. So let's look at an example that we could sort of understand what I'm saying. So we know that, say, the integral from 0 to 1 of x squared dx, we know that it's 1/3. We've seen this a gazillion times. It's a very simple integral to compute. And by the way, for full disclosure, let's just remind you this is approximately 0.33333. Obviously, that goes forever. So what if we used Riemann sums? So using a Riemann sum, what can we do? So let's approximate. So I'll say using right Riemann sums. Now you might have to review some of this. So what is the right Riemann sum? We know that this integral from a to b of f of x dx, we know that it's approximately the sum. K goes from 1 to n of f evaluated at x sub k times delta x. Now we can write this out to make it a little easier. What is this equal to? This is delta x. And then what is this sum? You have f evaluated at x sub 1 plus f evaluated at x sub 2 plus all the way up to f evaluated at x sub n. And what's important to remember, and this is the part most of you forget, is that delta x we were defining to be b minus a over n. And x sub k is equal to a plus k delta x. So we first encountered this way back in Calc 1 when we defined the integral. In fact, our definition is just the limit of this Riemann sum. Yes? Yeah, you would go from, say, 0 to n minus 1. Yep. So the question was, what if you use the left Riemann sum? Well, a left Riemann sum, you would start k at 0 and go all the way up to n minus 1. Yeah, for a left one, yes. Well, okay, and don't forget, too, that if you wanted to do, say, 10 rectangles, then you would go from, say, 0 to 9 if you did left. And if you were doing the right, you would go from 1 to 10. And the best way to see that is to draw it. and then you could see exactly what we mean by the rectangles. Okay, so let's apply this formula. Let's apply this formula to the function f, which is x squared. And let's just do this for some different values of n. Now, I'm not going to do them all by hand. I'll do n equals 4 by hand, and then I'll do a bunch of them using the computer. So let's just, let's go right ahead. And so let's say, okay, so for this guy, 0, 1 of x squared dx, what do we have? We have f of x equals x squared. We have delta x equals 1 over n. And what is our x sub k then? Our x sub k is going to be a plus k times delta x, which is, if we write this out, since a is 0, we end up just getting that this is k divided by n. So I know that there's a lot of abstraction here, but look, you guys, at this point, we need to start transitioning and to be able to do this. So let's just compute a couple of these. We'll do 1 or 2 by hand. So let's start with n. Let's say n equals 4. When n equals 4, I know 0, 1 of x squared dx is approximately 1/4 times, so it's going to be, we'll write it out slowly. We'll say x sub 1 squared plus x sub 2 quantity squared plus x sub 3 quantity squared plus x sub 4 quantity squared. Now remember, there's a quick way of doing this if you recognize the pattern. So the pattern is that, okay, when I plug in my x sub 1 and x sub 2, this becomes, every one of these guys, so this becomes 1 over 4 squared plus, I guess maybe I'll write it like this. And so this is 2 squared over 4 squared plus 3 squared over 4 squared plus 4 squared over 4 squared. And of course, you can clean this up. This is 1 over 4 cubed. I can pull out, and then you're left with 1 plus 2 squared plus 3 squared plus 4 squared. Now, we had a formula to do this quickly. Remember, I know for those of you who had me in Calculus 1 at the end of the semester, I know we've done it both in the spring and in the summer. We took our time and we recognized that there's this pattern here for x squared, and we could take advantage of it. And so what's important to note is, okay, cool. What is this? Well, we had a formula. How do you do this? Well, the sum of the first n squared guys is, does anybody remember it? And if you don't remember it, give you a hint, it's divided by 6. So, you know, we had a couple formulas we asked you to know. And one of them was this. So what is it? It turns out that it's it's n times n plus 1 times 2n plus 1. So this is 4 times 4 plus 1 times 2 times 4 plus 1 all over 6. And for the sake of time, we'll just tell you what this is. This is what? You don't want to get out of here. So what do you end up getting? You have I mean, you could go to a calculator if you want, but you end up getting 5 upstairs times 9, which is 45, 45 over 6, and then that's times 1 over 16, right? If you cancel the 4s. No one's saying you should do this in your head, but if you go to a calculator, it's not that bad. So what is it? So you have 45 divided by 6, and then times, I guess I can do 16. So if you do this, you end up getting, I believe, 15 over 32. Yes. The formula. So yeah, what I'm using, the formula that I'm using that we talk about from back in the day is that 1 squared plus 2 squared plus 3 squared all the way up to n squared is equal to n times n plus 1 times 2n plus 1 all over 6. That's where I got that from. So by the way, we can, from what we got from this problem, we can sort of just use that formula and we can get a bunch of values right away. Before I do that, before I go to the next page, does anybody have a question? Okay, so here's what we know. So if we recognize that pattern, we got this. So if we recognize the pattern, we conclude that the integral from 0 to 1 of x squared dx is approximately 1 over n cubed times n plus 1 times 2n plus 1 over 6, which if you clean this up, you're left with n plus 1 times 2n plus 1 divided by 6n squared. So we can make a little table and we can think about how these approximations work. So let's make a table here. And so if in the left-hand column, I'll put my values of n. Question? Well, right, that's the point. So what do you mean never? Who said never for what? What is never, Emily? What is never? Now I don't remember. So yeah, Zafalgar, you're correct. The larger n, the more precise you get. So when we did n equals 4, we got 15 over 32. What's 15 over 32? So this would be, the integral here. You're left with 0.46875. And then if we plug in 8, or even heck, we can even, we'll square it. We'll go to like say, or go to 20. Even if we go to 20, you get 21 plus 41 divided by 6 times 20 squared. So what happens when you do this value? You end up getting 0.35875. So it took us, we're not even at 2 decimal points of accuracy, and it took us 20 rectangles. What if I go up to say 50? So if I go to a calculator and I compute this for 50, well, this would be 50 times 2 is 100, so this would be 101. And then this would be 51. So still, with 50, I'm still at 0.3, but I don't have an agreement in the second decimal place. So what if we do 100? So if I do 100, I'm now at 0.33835. So we know this thing's going to a third, but it's taking a long time to get there. So that's sort of what the point we're trying to spell out to you. And that is, it's taking a long time to get accurate, if you will. So then once you realize it's taking a long time, and then you start to think about the problem, you might realize why it's taking a long time. If you graph the situation, you realize that there's going to be lots of error because our curve is steep, and we're using rectangles. So with anything, we ask ourselves, can we do better? And so obviously the answer is going to be yes, but then the bigger thing is not just that it's yes, but why and how. And again, better is a relative term, so we're best putting that in quotations. So here's a thought. So perhaps we use midpoints instead of the left or right? So let's draw a picture of what I mean by that. So if I sort of draw this x squared here, so let's say that this is 1, and of course, oh, that was bad.
That's all, right?
We'll say that again.
That's all. Left or right?
Left or right? Yeah, that's an R. I'm sorry. Yeah, let me fix that for you. This is O'Grady's very poor R. Okay, so what is this? What does x squared look like? Well, we know it kind of looks like this. And so let's just draw what happens when we're using 4 rectangles. If we use 4 rectangles, right away you see why there's some air. You have this rectangle, you have this rectangle, you have this rectangle, and then of course you have this rectangle. So one way you might describe this is you might say that this is an overestimate, as we saw in our calculations. Is that right? All our estimates were above 0.333. They were getting closer, but it was taking a long time. And the reason for that is you have sort of this excess, all this extra air here. And so what if instead, if instead of doing that, we said, okay, well, let's try to do better. And let's try to draw the same picture. And instead of using these right endpoints, what if we used midpoints instead? So I draw my rectangle, I break my interval into 4 pieces, but instead of using these right endpoints, so let's remind you of what this is here. This is 1/4, 2/4, 3/4. And that's what these creatures are right here. I mean, these are still 1/4, 2/4, 3/4. But for the height of my rectangles, what I'm going to choose is I'm going to choose the midpoints of these. And what happens when you do that is you end up, at least in this scenario, having some of the air cancel out. Because even though I have some overestimate, I also have some underestimate. So we might say that this is a better estimate, maybe. See, and not only do we not know for sure if it's going to be better, in this particular picture it looks better, but that's because the nature of this curve as it's increasing. But what if the curve was flatter or it was decreasing? Now, not only do we say, okay, it could be better, and let me emphasize why I'm saying it's better. Because if you look at the left-hand side, you have lots of air. Over here, you have a little less overshoot, but you also have some undershoot. And you might imagine that they sort of cancel each other out. Now, the downside to this midpoint is we'd have to compute 4 more points. So while it's possible that this could be better, there's no guarantee based on the shape of the curve. And not only is there no guarantee, but even if it is better, we have to do more work. Because we'd have to do, if I have 4 rectangles, now I need to compute 4 more numbers. I'd have to compute the midpoints. If I had 20 rectangles, I'd have to compute 20 more numbers. Right? Do we understand this? So I'm not saying this is bad. You can do it. So this method, we touched on briefly in Calc 1, is called the midpoint rule. Now, it's possible it's quote unquote better. However, as I said, it requires we compute more points. So even though if we think it's going to give us a better approximation, the downside is we have to do more work. And I don't know, you're like me, I'm like you, the less work, the better. Wouldn't you agree? I mean, think about it. The midpoints, what is the midpoint? And this is going to look scary, but what is the midpoint of the interval? Say we have the interval x sub k minus 1, comma, x sub k. What is it? Well, how do you find the halfway point? You have to add them up, so you take x sub k minus 1 plus x sub k, and then you have to divide them by 2. That seems like a lot of excess work, at least for a human, and it could be even for a computer. And so as my buddy Obe likes to say, is the juice worth the squeeze here? Even though we think the approximation will be better, we're still doing more work, even if we don't think we are. Yeah. Because remember, when k starts from 1 to n, so when k is 1, you'd get x of 0, comma, x of 1. Right? Remember, so that's a good question. The question was, why did I put k minus 1? Well, I want to write a rule down in general. Right? So what's m sub 1? M sub 1 is x sub 0 plus x sub 1 over 2. Then what is m sub 2? It would be the next interval. Don't forget, your interval looks like this. This is x sub 0. This is x sub n, and then don't forget x sub 0 is a, and x sub n is b. And so then you have your x sub 1, you have your x sub 2, and then, for example, we would call this point in here, this would be your m sub 1, this would be your m sub 2. Does that make sense? So we still have to do more work. Now, of course, if you know anything about programming a computer, it's not hard to get a computer to do this quickly. But then the question is, can we do better? Now, I'm not going to go through this because it's very much the same as the right Riemann sum, and it's very much the same as the left Riemann sum. If you want to do it on your own to convince yourself, that's fine. But we need to get to the punchline here, right? There's got to be a better way, or I wouldn't keep saying this. But before we do that, does anybody have a question? Preguntas, anybody? Going once, going twice. Sold. Check my time. I'm looking at the time on my phone, yet it's right in front of me on the computer. It's a strange world we live in, right? I wear a watch usually, and I don't even use it for anything. It doesn't even have the right time. I just look at your phone for everything. Okay, so what we're going to do on the next homework is we're going to ask you to write down the right Riemann rule, like a right sum, a left sum, and the midpoint sum. They're very much the same. We already did the right one for you at the beginning. Midpoint and left are, like I said, they're very much identical. And they're actually, in many ways, they're ancient sort of algorithms. As you would imagine, humans have known about these for quite some time. So we'll let you practice that. And of course, if you have questions, you can ask and we'll talk about it over the next few classes. So here we go. Let me remind you that of this point that it requires we compute more points. So let's ask ourselves, can we do better without computing midpoints? And then this is kind of the question that it'd be great if I went to a 5th grade class and I said, what would you do to get better? You know, the 5th grader, they would get it way quicker than you guys would. Because they don't overthink things. The 5th grader says, well, this is bad, right? And then the 5th grader says, this is bad, and yeah, they might cancel out, but they're going to say, why don't we just kill them without worrying about it? And the 5th graders are much more used to dealing with other shapes than maybe you are as a university student. And then the 5th grader says, duh, why don't we try a shape that's more useful? And then the first thing that comes to mind to a 5th grader would be, why don't we try a trapezoid? Let's see who guessed that. Lies. I don't know why we're saying this. See, Emily, you got to time these in. I need to know the context of my never and my lies, right? Although, I hear you. Anybody have any funny jokes? I didn't say a 5th grader is smarter. See, you only heard what you wanted to hear. I said a 5th grader doesn't overthink things the way an adult does, myself included. It's not just me. It's not just you. What we often do is we often overthink things. I'm like looking out the window. What if there's like a 5th grader just banging on the door? Don't ever do that. All right, so let's go over here and let's say, okay, is this gonna be good, Eric? I don't know. How do I count cows? Let's see. How do I count cows? Moo 1. I don't know. What is it? Let me hear it. There you go. See, that's a good one, right? What do you call a pot of water boiling on a stove? A high pot in use. Get it? Dinner. That's a dad joke. That is true. Very good. That is a dad joke. Although I should start sharing with you the fun conversations that I have with Lydia on our way to school. Right? She's 5. She has the best questions. We'll share them one day. All right. So here's the answer. The answer is, let's try a simple trapezoid. So what we'll do is we'll draw this out and say, oh my God, O'Grady's on to something, and the 5th graders. These crumb snatchers are on to something. So if I draw my sort of my x squared, my quadratic again. Let's break this guy into 4 pieces like we know we're supposed to. This is 1/4. This is 2/4. This is 3/4. Let's get our blue. Let's graph it. Oh, that was bad. Go away, you terrible, terrible creature. So now, what we're going to do is we're going to do what we normally would do. We're going to draw a line from here to here, and a line from here to here, and a line from here to here, and a line from here to here. But instead of us using rectangles, we're going to use trapezoids. So I'm going to draw this line. And then I'm going to draw this line. And then I'm going to draw this line. And then I'm going to draw this line. And now I have 4 trapezoids. And this looks, quote unquote, looks better than a bunch of rectangles. Now, of course, you might argue that I didn't draw this thing properly. I'm just sketching it, and that's true. But we can do the computation to see how much better or worse we've gone. Does anybody have a question? Now, the only thing you got to remember, Emily, and I guarantee the 5th graders are more likely to get this right. Don't you remember that, Schmo? Are you smarter than a 5th grader or 3rd grade? 5th graders more likely to not have to Google the area of a trapezoid. We have to Google it, right? Because we forget what it is. You're going to have to say, I don't remember the area of a trapezoid. I'll tell you what, 5th grade me was I was a hell of a student. Mrs. Cooper. I don't actually, do you even do trapezoids in 5th grade? That's probably not. Trapezoids are probably like 7th grade or something. I don't know. Do you remember? I can't remember what I had for dinner yesterday. No, I shouldn't say better, better than. I got to learn how to spell better. So let's do the computation. We need to know the area of a trapezoid. So it turns out, let me just draw the picture here. If we just look at, say, this one, we'll call this, I can't write it in there, we'll call this a sub 2, we'll call this a sub 3, a sub 4. So the key observation is that if I have a trapezoid that looks like this, if my trapezoid looks like this, and let's say that this is, you know, its width is, we'll call it W, and then we'll call this A, and we'll call this B. So what's the area? The area here is you take the 2 heights, A plus B, you divide by 2, and then you multiply by the width. That's the area of a trapezoid. Now we need to apply that to our picture here. So here's what we have. Notice that we're going to have to count this point, this point, this point. So we need to know all these points right here, but we know them already. These are the functions output at the inputs down here. So what do we end up getting? So we get the integral from 0 to 1 of x squared dx. Well, what is it? Area 1 is, it's going to be, so maybe we'll write this out. Okay, so what is it? What's the, you know, this is going to be A1 plus A2 plus A3 plus A4. So what's the first one? Well, it's going to be the height, which is 0. It's going to be 0 plus, what's the first height? It's 1/4 squared over 2. Then the next one is going to be 1/4 squared plus 2/4 squared over 2. Now the next one's going to be 2/4 squared plus 3/4 squared over 2. And then the last one is 3/4 squared plus 1 squared over 2. Now every one of these has a width of delta x, so that is 1/4. Now, let's not overthink this. This is, how many of these creatures are there? Well, the 0 goes away, so we have a 1/4. If I put everything over their denominator, what do I end up getting? I get 1/4 squared plus 2/4 squared plus 3/4 squared. Now, the only guy that doesn't have a partner is the last guy, 1/2. What's that? Well, look at the 2. So the question was, what happened to the 2 on the bottom? Well, this guy has a 1/2 in front of it, right? This guy has 1/2 in front of it. When I add them together, there's one of them. Now, the reason there's a 1/2 here is because this very one at the end doesn't have a partner. The rest of them all have partners. Now, let's just go to a calculator. I mean, I could look for the pattern here, but it's not going to be worth my time. I guess I shouldn't say it's not worth your time. It actually is, but we're in the we're running low on time in class, so I'm just going to go to a calculator. And do the sum. So what's nice about this is if I do this correctly, I get 11 over 32, which is approximate. Well, it's not even approximate. It's equal to 0.34375. So with just using 4 trapezoids, we are already 1 decimal point of accuracy. So, does anybody have a question? Now, I'll save you the fun. You're going to finish this for homework anyhow. What happens if instead, if we use for n equals 8, what you'll get is 0, 1 is this integral is approximately 0.33. So in the previous, using the right Riemann sum, it took us nearly 20 to get 2 decimal points of accuracy. Here with 8, we have it. So if you compare this with the right, So if you compare with the right sum, when n equals 8, when n equals 8 with the right sum, we got 0.3984, I believe. Let's check. We have to go back a couple pages. Oh, we didn't do that, but you would have. See, with even 20, no worries, Muhammad. With even 20, it took us 20. It took us 20 rectangles using a right Riemann sum to get 0.33. All right, so does anybody have a question about this? So one of the things you'd like to be able to do is you'd like to sort of make a table of this. And so we could summarize this. And it turns out that who was that? Instead of blaming anybody, we just mute it, then we don't blame anybody. We never know whose fault it is. Bebe's kids. Remember that? Anybody know that? That's before your guys' time. Damn. All right, so here's what I need you guys to think about for next time. So food for thought. Now, of course, you can look this up. First off, is there a nice formula for using trapezoids? And the answer is going to be yes. What is it? And then the next question is, can we do better? Right? We always want to do better. We want to be more efficient. And the question is, can we? And obviously, I wouldn't ask this if you couldn't. So yeah. So we'll talk about this thing called the trapezoid rule, and then we'll also talk about a slightly more sophisticated algorithm called Simpson's rule. I should point out that if any of you are in computer science or in engineering, you should really give thought into, can you use a computer to do this? It's not hard to do. Now, I mean, of course you can do this on Desmos, but I mean things like, can you program a computer to do this? And I can show you how if you want. One of your extra credit assignments will be to write some scripts that do this real quickly. Just to give you a heads up on what that might look like. If I go to my computer real quick, let me share something with you if it loads up. Now, I'm not sharing this to frighten you, but there's what you can do is you can write some code using whatever your favorite language is. And I can share this with you. So here's something that does this code right here will integrate left Riemann sum, right Riemann sum, and midpoint. So basically, I'm going to tell it to integrate x squared from 0 to 1. And let's say I use, like we did before, how about we use 8 rectangles? And if I run it, you'll see that the left Riemann sum 0.27, right Riemann sum 0.39, which I just said, and then the midpoint 0.33. But then I can do even better if I use a different file, which is a little more sophisticated. You'll notice at the bottom I have it doing a left sum, a right sum, a midpoint, trap, and then what we're going to call Simpson's rule. And it's not hard to learn how to do this. If you know Java already, you can do this, although it's not as easy in Java as it is in this language. but it's something that if you're an engineer in computer science, you should know how to do this kind of stuff. I mean, it's not part of this class, but you should know how to do it. All right. So I'll share any code you want. I'll be happy to meet with you and show you how to do it. Anyhow, we're out of time. Someone's chatting. This is called Octave. And Octave is a free version. It's called a clone of what's called MATLAB. So what I'm using is Octave, and it's a free clone of MATLAB. MATLAB is sort of the staple #1 software in computation. Lots of people use engineering, companies, but MATLAB's expensive. So this is a free version of it, and it gets the job done. So if I run this, for instance, this script, what it's doing is it's integrating something, and it's, this code will do it for, notice I had to do it for what? 4 subintervals, then 64, and then 1,000. And one of these things I'm doing is I'm trying to determine the value of pi using an integral. You'll see that 3.141. Anyhow, this is it's pretty simple to learn. It's free to download. If it's worth learning, it's not hard. A lot of people, I think Python has a lot of built-in stuff. If you want to, that's another staple that people use, Python. I think with Java, you have to import a bunch of different type of sort of other programs that do math. All right. Anyhow, if you have questions about it, I'd be happy to answer it. If you guys don't have any questions, I will say Godspeed, as they say. And I will talk to you and see you soon. Thank you guys very much. And I will post a new homework for you. Take care. Thanks.